Okay, Christian, over to you. You can start the meeting. Welcome everybody to day 2 of our conference. I'll hand over to our Vice President, Christian Popin, who is going to introduce the day for us. Thank you.
Okay, thank you, Robert. So good morning to everybody. So when you look at the agenda, you can see I am supposed to speak 15 minutes, but don't be afraid, it will be really shorter. So it's really a pleasure and an honor to open the second day of our 60th anniversary celebration. GERG is a pioneer organization, the first gas association in Europe. Over 60 years, this community has grown, adapted, and continues today to be active and focused on new challenges in order to develop energy solutions for next generation. So even if I couldn't be with you yesterday, I know we had very interesting presentation on methane emission and how we can mitigate them. So the program we put together with GERG members and partners for the second day will enable, I'm sure of that, very fruitful exchanges on the second strategic subject, biomethane, or how fossil methane could be replaced by renewable one to efficiently tackle the global warming of our planet and succeed in the energy transition. So this morning we will have a pleasure to listen to a presentation of a GERG biomethane research roadmap developed by our biomethane working group. After we'll have the SEN biomethane project, a flagship initiative for GERG, and the PRCI renewable gas gap analysis. After the coffee break, a focus on bio-LNG will be shared with you. And to end this day, a panel discussion with knowledgeable experts will consider how to lift obstacle to the increase of biomethane injection in our energy system. So let me wish you a good day, and I give the floor now to Torben, the leader of GERG Biomethane Working Group, for the first presentation.
Thank you very much. And welcome to this session from my side as well. Alexander, I'm trying to change the go to next slide. It doesn't work that well for me.
I can do that if you prefer, Torben.
Yeah, please, because that's necessary. I'll present, as our Vice Chairman just said, the roadmap, R&D roadmap for biomethane for you. Next, please. As you know, biomethane is very interesting for gas from a gas system point of view, as it can contribute to decarbonize the energy system. It can be regarded as carbon neutral or even carbon negative, depending on the biomass resource, the biomethane production process, and also factors as carbon capture, CO2 utilization, and things like that. Why have we in GERG prepared this roadmap? The very brief answer to that is that we would like to emphasize or get the most out of the work of GERG. The roadmap will provide a detailed prioritized list of research topics for the members to start forming projects, and they will also be aligned with the other initiatives, therefore enabling cooperation or funding opportunities. Furthermore, the roadmap, they will serve as a communication tool to attract partners from outside and to promote the work outside our own members. Next, please. As you probably heard, we have 3 sets of roadmap that are being prepared. One on methane emissions, one on biomethane, and one on hydrogen. And today I'll shortly take you the one on biomethane. We've had an ongoing project for the last year or something like that, where the roadmap has been defined in close cooperation and interaction with the people from the gas industry. We've been through a brainstorming phase where we identified possible R&D subjects, a phase where the projects were defined, and we have evaluated how critical the different subjects appears to be, and based on that we have created the roadmap. So the next step will be to execute.
Sorry to interrupt you, but maybe we can recall the rules, if we can interrupt or ask question, or if we have to wait for the end of the presentation, because I saw that there were a hand up and maybe someone wants to ask something. So Robert or Alexandra, could you recall the rules for this morning?
Well, I think the intention today is that if people have a question, they can either, I think they use the chat. The chat is open today, I believe, on Teams. Alexandra confirmed that. We didn't use it yesterday. But if there is a question, I don't know, I see Laurent Benoit has his hand up. Is there a specific question, Laurent, that you...
Sorry, it was a mistake of mine, but it was a... Sorry.
Okay. In general, we perhaps... we will take questions at the end of each presentation, either through the chat or through raising of the hand. And of course, as usual, it will help for bandwidth if people keep their cameras switched off if they're not speaking. And ideally, everyone should mute themselves if they're not speaking. Otherwise, you might find someone else mutes you. But yeah, if we use either the chat function or raised hands to ask questions, we will take questions at the end of each presentation. I think that should be the rule today, if everyone agrees. Thank you.
Okay, next please. Here you see the whole value chain from biomass collection to the production, to billing, to utilization. And the objective of this roadmap starts when the biogas is produced. So it's from gas cleaning, upgrading, all the way to utilization. That's within the scope of our work here. Next, please. Okay, so how did we do it? We've had a pretty intensive process where experts who are members of the working group have been very active in a process that were facilitated in a very professional manner by the people in the GERG Secretariat. Pretty early in the process, we decided to divide the topic into two main categories. One being the whole production value chain, and the other is the gas qualities. And in the value chain, we have 4 subcategories: upgrading, gathering, injection, gas storage, and methane emissions. In the gas quality, we have overall composition, impact of siloxanes, sulfur and terpenes, safety, authorization, analyzers and meters, and finally billing. We had a number of virtual workshops. That was what's possible in these Corona times, and it has worked surprisingly well, I think. So for each of the 11 subcategories, the working group members could place a virtual sticker on which they have written a potential R&D area. And then they could place this sticker on a virtual board. And when all people who wished to place a sticker had done that, we went to a kind of voting session where the participant put their votes on the different stickers according to what they found was the most relevant and where the largest requirement for demonstration and development were. Next, please. Based on the outcome from that process, a very draft roadmap were written by the Secretariat, and that included a suggestion for a timeline for each of the 11 subcategories. An example of such a timeline is shown here for the category analyzers and meters from the gas quality section. And you can see the first shown here is the low-cost oxygen sensors for billing purposes. Next consists of 3 interdependent subjects, where the first being defining the requirement for the gas operators need to check the gas quality, performing a benchmark of existing and developing analyzers, and the last in this 3-step is defining best practice for measuring the different trace components. You can see most of them here is marked in green, one in blue. The green ones are the one we have defined with the priority high, and the blue are the ones defined with the priority minimum, or medium, of course. Next, please. Here you see some of the selected high priority areas. I will not go through them all, just mention a few of them. For the value chain, I would like to highlight 2 areas that I find especially important. One is the review of upgrading technologies, the pros and cons, because beside the biogas production itself, it's the most costly step in the whole biomethane process. And reducing cost will ease the way for further biomethane into our gas systems. Another crucial issue is the impact of biomethane on greenhouse gas emissions. We need to be able to tell a trustworthy and well-documented matter the climate impact of biomethane, depending on the process, feedstock, etc. And as a part of that, we need to limit methane emission, of course. Regarding gas qualities, then we need to ensure that the biomethane can be used safely without damaging the appliances that uses the gases. Therefore, we need more information on which feedstocks that lead to which trace components in the gas. That might be siloxanes, terpenes, and furthermore, we need to know to which extent we need to remove the trace components and what concentration levels can be accepted. And that is something I guess we'll hear more about in the next presentation. Next, please. Because this leads me to the conclusions. Yeah, the biogas and biomethane sector is a valuable asset for the transition of the gas system and the energy system in general. Collaborative R&D work and knowledge sharing is the key to ensure this required development in an efficient way. The GERG roadmap here is an example of such a initiative that follows up actions that are already ongoing. One is the biomethane injection best practice process. It's right now being defined, and yeah, we're soon ready to execute on that one. Based on all this, there will be a report that will be available for GERG members on the webpage, and we have made the Secretariat have made a brochure, the one depicted on the slide here, and that is available at the homepage right now, and it's publicly available. So thank you for your attention. And if you have questions, you could please raise your hand. Well, okay, if that's not the case, then I think I will give the floor to Marine. Are you ready to start, Marine?
Yes.
Thank you very much.
Hello, everyone. So I will present you today the GERG biomethane project, on which one we study the impact of the trace component on the different gas infrastructures in this project. Alexandra, can you move forward, please?
Yes, sure. Marine, if you want, you can also take control of the slides, or I can do it.
Okay, if I can do it, it's perfect. And so, as you may know, two standards have been published in 2016 and 2017 about the natural gas and biomethane specification for its injection into the natural gas grid, and also for another application, that is the automotive fuel specification. And in these standards, we have some limit value for trace components such as siloxane, hydrogen, oxygen, sulfur, and so on. And in I'm sorry, Alexandra, I cannot change this.
Take control.
Yeah, maybe it's okay. Yes, thank you. And so we have been working with all the gas operator and also with the European Commission, and we put all together our priorities and worries about the biomethane in order to conclude on what could be the impact of the trace component. And the main objective of this project is to offer the condition to a safe development, but also a competitive positioning of the biomethane chain. So it is important to have a limit value on some component that could impact the safety of the gas infrastructure, but we have to find the good value in order to not increase too much the biomethane production cost in order to kill the pathway. And so it's really the point of the project to find the good value between these two objectives. And with all the data that will be assessed during the project, that will allow us to provide data for the reviewing of the standards that will be automatically be launched during next year. And so the whole methodology of the project is first of all to identify the trace components that could be a source of concern, and focus on this trace component. We identify the gap of knowledge on their possible impacts in order to not redo what already have been done in the past. And if we have a gap of knowledge, we perform an experimental program in order to have new data to answer on the limit value. And so the project started a few years ago now, in 2017, with the GERG industry priorities. So at this point in the phase 1, the European Commission was not involved in the project, and we performed the really first step of the study. That means identify what are the trace components that are a source of concern, and start with the gap analysis. The conclusion of the phase 1 was that the main trace component was the siloxane and the corrosive components, and also microorganisms, and we have a gap of knowledge on this one. And so we have built the phase 2A in collaboration with the same priorities. And this phase 2A started in 2018 and 18, yes, to end in 19. In this phase 2A, we have studied the literature survey on the impact of sulfur oxygen and also on health impacts. And we have performed an experimental program on siloxane. When the phase 2A ends in 2019, we have concluded that there is a gap of analysis based on the literature review, but still on the siloxane impact. And so we have launched the phase 2B of the project that officially started in October 2020, in which one we go further in the detail for the impact of each component. And this phase 2B will be completed with, we hope, a phase 2C that is still under construction in order to have a complete overview. And all the work that is performed in this project will be used in the revision of the standards that will occur in 2022. The project has also a supervisory board in order to have a complete validation of the results of the project by different gas operator. So in this supervisory board, we have the European Commission, of course, the CNTC408 members, some biogas association, and also end users. So we have gas operator, we also have engine producer, and also boiler producer, for example. If I go further in the detail of the results of the phase 2A, on the siloxane impact, we have performed experiments on both application, industrial boilers and heavy-duty engine. And so in both cases, we have seen that, yes, we can have a white deposit of siloxane in the coldest parts of the systems. So as you can see on the pictures, but we haven't seen any failure of the boiler or of the engine during these tests, and we have performing quite long tests. So we are quite confident to have maybe a higher value of siloxane, but this conclusion needs to be confirmed by the new experiment that will be performed in the phase 2B of the project. On the sulfur impact, so as I said earlier, we only performed a literature survey, and so what we have seen is that when it's not the sulfur only that poisons the after combustion system and the catalyst more precisely, it's because we have sulfur with oxygen or with water, and this reacts, and this is this reaction that poisons the catalyst. And what we have seen in the literature review is that yes, there is some studies on the impact of sulfur on ATS, but not much at the concentration that we can have in the biomethane. And so we need to go further with an experimental program in the phase 2B and phase 2C in order to really understand the mechanism and to assess what could be the concentration limit that can be implemented into that standard. And so there is quite a lot of work to perform on this point. On the impact of oxygen, we are studying it from two axes. The first one was the impact on underground gas storages, and we only perform a literature survey, so no experiment for the moment. And what we have seen is that, yes, the presence of oxygen could be a source of nutriment for the microorganisms that are into the underground gas storages and mainly in the aquifer one. And this oxygen can react with the microorganism in order to produce H2S. And this H2S increases then the acidity of the underground gas storages, and this is what can prematurely deteriorate it. But it's what we think that can happen in the underground gas storages, and we don't have real knowledge on what are the mechanisms and what could be the degradation mechanisms and so on. And so that's why we will go deeper in the phase 2B and phase 2C in this project in order to perform experiments to have more answer on what are the mechanisms and what could be done to limit these mechanisms. And we also study the impact of oxygen, but also other corrosive components on the pipelines for the gas transport. And so, yes, we know that water with corrosive components can cause some problems on pipes and corrosion problem, but we haven't seen in the literature so much information that cover the underground gas storages and the transport conditions also. So we will perform a complete experiment on this point 2 in the phase 2B and phase 2C of the projects. And so in the phase 2B and phase 2C, so as you have seen, we performed a lot of work in the phase 1 and phase 2A of the project, and we still have work to do in order to have real answer for the revision of the standards. And so the European Commission should fund the next phases of the project. For the moment, the phase 2B is funded around 2 million euros and the phase 2C around 3 million euros, and we will have a complete proposal for next year. We have some delays with the European Commission that changed the rules to get this money, so we handle it with Robert this year, but it's quite challenging. But we hope that we can really perform this phase 2C. And so we will have an experimental program still on siloxane impacts, both on industrial boilers and on heavy-duty vehicles, in order to have more precise information on the oxygen sensor, for example. And in the sulfur impact, we will also perform a complete experimental program at laboratory level. First of all, we will test several catalysts with several H2S contents. Then, based on these results, we will perform engine tests with just 1 or 2 catalysts in order to have real condition conclusion. And we will also perform aging tests, so on a very, very long period, in order to see if there is any failure of the catalyst based on the H2S content, and also in order to see if we can increase the H2S content limit in the standard or not. And we will also perform some modeling work in order to see if we can anticipate the deterioration of the catalyst thanks to a numerical model. And all the contributors of the next phases are quite the same of the previous phases. We have two new contributors that are the DBI in Germany and RISE in Sweden. We will also perform experimental program on oxygen and corrosive component in both applications that are underground gas storages and on pipes. And we also have added a new work package in this program in order to improve our biomethane knowledges, and mainly on the biomethane composition data and what we can have in the different countries in Europe. So we will build a huge database based on data from UK, Sweden, and France. And we will also complete this database with trace components that we can have into the bio-LNG. We also had a study about the biogas treatment technologies, and we will study it from an economical point of view in order to anticipate if all the limit data that we will have in the standards can increase or not the biomethane production cost, and what could be the impact for the development of the pathway. So we have quite a lot of work to do, as you can see on this timeline. The phase 2B started in 2020, to end in 2022, and the phase 2C should start next year to end in 2024. And all the work that will be done in these two phases will continuously help the CNTC4 rates on the revision of the standard, and so we will provide data all the way long on this project. So thank you for your attention, and if you have questions, do not hesitate. I'm sorry, I think that...
May I put a question?
Yeah.
Nikolai Kadensky, Head of Network Development Department, Guest TSO of Ukraine. In Ukraine, we have been proceeded some changes in our law, so biomethane got this definition in energy law, so we started preparing secondary legislation, and as a guest TSO, we have been found great interest from agriculture business to, you know, create a biomethane production. And for sure, we understand that right now we're facing these uncertainties with oxygen content in a biomethane or in this new gas. And for me, the question sounds like this. So we understand that we have in Ukraine some sensitive consumers, which are, you know, sensitive to oxygen content. Maybe it's fertilizer plants or glass production, but we don't still understand the full list of this sensitive consumers. I found very useful idea or say this in your presentation or not in yours, but somewhere, that during today's meetings that oxygen removal could be cited at end users locations. For me, the question is, what about interconnection agreement? How to deal with oxygen content when in one country you have this content, and here on the border, you know, let's say you have requirements with another oxygen content. Do you have some, maybe insight, some ideas, what could be the strategy for, managing these the risks?
Well, it's a quite difficult answer, I guess. It's what we are trying to do with this project is to have a consensus for all the European countries on what could be the limit value on this trace component, and more precisely on oxygen. So one thing could be that all the European countries base our own law on this standard in order to have an homogeneous gas composition into the network. This is one point. Another solution I can see is that to have a specific gas treatment on the interconnection point, as we can have one between gas distribution network and gas transport network. So this can be also a solution. I guess that this have to be studied at the European level to have an homogeneous oxygen content into the gas.
Okay, so maybe the last question, just to clarify, what is the oxygen level in your country or in your companies? What is the requirement for oxygen level? Do you have some maybe list of oxygen level limits in a different TSOs or different grid codes in EU?
Yes, I guess that we have a specific working group on oxygen, Robert, I think, and they performed a study on this point, and to have an overview of what are the limits in Europe on oxygen. Maybe I see that Xavier Campagnol from Storage is here and is quite active in this group. And so I get that there is some studies on what are the limit value on oxygen. I can send it to you after all.
I will be very grateful for this information, because actually on tomorrow we scheduled a meeting with 24 of potential pilot producers of biomethane, because Ukrainian potential for biomethane accounted for more than 7 BCM. Because of our big agriculture potential, 7 BCM of biomethane, and they want to produce, but we are trying to find a match on this oxygen because it's never have been done before. So my name Nikolai Kadensky from Guest TSO of Ukraine, head of network. I hope you could share with me this info report or something on this oxygen content in EU, and how it connected with, biomethane development, because for us it's very important right now. I'm very, grateful, and thanks to everyone that you share this information with us.
Okay, we'll try to collect data or see what we have, and then you can send. And if we don't have your we have your contact info, so in GERG we can send it to you if we find some.
I mean, Torben, I noticed that Eric Buthka, the chair of TC408, is with us in the meeting today. I don't know if Eric wants to make a specific comment. I mean, I think there's quite a lot to say about oxygen, whether it's at transmission level, at underground storage level, or at distribution level, where you do get derogations to the regulations sometimes for biomethane, and you've seen that in places like the UK. But I'm not sure if Eric wants to make a comment. I mean, Eric was instrumental in setting the kind of boundaries for this piece of work that we're doing. So perhaps you would like to make a comment. Sorry to put you on the spot, Eric.
No problem, no problem. Yeah, the focus on the standardization is really on how to implement biomethane as a fuel into the network, and to specify the trace components. So it was clearly explained by Maureen how the research program is going on. In 2016, we used some old research what was done at that moment, And during the whole process of standardization, we figured out that not all questions could be answered. And that's the reason to start this new research project and to study more in detail how to come up with limit values. There's also a big difference in the whole approach of this standardization, because we make a very big difference between the standardization of fossil natural gas, which is that standardization is already done in other groups. So we only specify the trace components which are available in biomethane. And for that reason, we have also close cooperation with the other standardization groups on just distribution of the traditional natural gas.
Okay, thank you, Ed.
Okay.
I can see there's a hand from Laurent.
Yes, it's a question connected to the question of Mikola. Just I wondered what are exactly the problem with oxygen? Is it only corrosive issues? From the Mikola talks, I understand that there are also issues dealing with final customer application, first. And second, just again, maybe I did not see correctly, but do you plan in the research program to address the oxygen removal strategies? Because it's probably also still an open field. So these are my two questions.
Well, the first question is that yes, the oxygen can be corrosive for the pipes. It can increase the production of H2S in underground gas storages. And what we have seen is that from some end users, such as glassmaker, we have discussion with them this year on other project, and yes, there is some problematic regarding the oxygen compound that can decrease the glass quality. I don't have the overall vision on each end user that can be a problem with the presence of oxygen.
Okay.
But yes, we know that it's a source of concern.
And about will you address the oxygen removal strategies, the technologies in your future research plan?
Well, in the project, yes, we have the last study of the project that is studying the removal technologies, and oxygen is a part of this study. So yes, we are studying it. It's already a study in a specific task force and in several research projects. For example, at NG, we are studying it, so it's already ongoing at this point.
Okay, thank you.
Thank you very much, Marine.
Thank you, you too.
But it's not only GERG who is looking at R&D gaps, and we will hear more about that. So, will you enlighten us on that, Amelie?
Yes, I'm online. So good morning, everybody. Sorry, I'm joining this meeting late. So thank you for giving me the opportunity to present to you. So a work realized by PRCI last year on renewable natural gas, state of the art and gap analysis. So maybe you can, maybe I can move to next slide.
If you take control, Amelie, you can, I think.
No, it's not possible for me. No, I don't have the control to change the slide.
Okay, do you have a take control button? on top?
No, I don't have it, but maybe you can change for me. It's okay.
Yeah, I can do it, no problem.
Yeah, thank you, Alexandra. So the objective of this project, realized in a couple of months last year, was to develop a concrete path to define what are the main project, the main, I will say, priority to complete for company to safely and reliably inject energy into their pipeline. So PRCI is composed by, I will say, gas company involved in transport or storage of gas. So we are only dealing with issue regarding transmission and underground storage level. So this I would say study will help to address a regulatory issue for natural gas utilities. Maybe we can change slide. So in the next slide, yes, I will give it to you an overview about the project team. So we had a core team, and it was 11 organization. All partners were PRCI members. So in Europe, so we had Gasunie in the Netherlands, Gasco in Norway, and GERG Gas, but also in North America. And we also contact other organizations in the world, so in North America, in Australia, and also in Europe, and the GERG was one of them, and helped us a lot to collect data and to review, I would say, the final report. And as we have an agreement between the GERG, the PRCI, and Future Fuel CRC in Australia, it was nice to have this collaboration. And I also know that some of the work done regarding both biomethane and hydrogen was used this year by the GERG, and it's really interesting to have this, I would say, collaboration and exchange. So I think you can change the slide. So how we work. So so our objective was really to identify, as I told you, the R&D needed for company to be able to inject renewable natural gas in their pipeline. So we choose to work in 4 steps. So the first one was a mapping. So the idea was to collect as much as possible document information on project related to natural gas. Then we were able to perform a state of the art regarding the data that we collected. We also perform a gap analysis regarding where we are today with the data that we have and what is missing to achieve the goal. And we were able to write a roadmap for PRCI. So we performed this project between April to September last year. We decided to study 10 technical subjects. So the first one, and the one I would say maybe the most important, because with this one it's related to LNG composition. You can have information on other also technical topics, and it was also the main one because it's the one that we collected roughly 50% of the document. So the first one, I told you, it was on LNG composition. The second was on injection and dilution related impact on gas grid. We have a small one dedicated to safety. The 3 following were dedicated more to the biomethane injection point, so analyzer, authorization, metering, then on a global injection system. We also collected a few, I would say, data on storage, and the 2 last topics were more, I will say, for the future. So it was reverse flow injection system and gathering line for biogas. Well, for these 2 topics, we didn't collect a lot of information, but it was also important to highlight that this topic could be important in the future. So maybe you can change the slide, please. So as I told you, the goal was really to establish a state-of-the-art on renewable natural gas and to create a common basis of knowledge between partners and to identify research and development gaps. And also the idea was to propose key projects for PRCI to work in 2021 and for 2022 and 2023. So I think you can change the slide. So yeah, this is one. I tried to summarize on this slide the work done. So we collected almost 130 documents. We were also able to list 60 RNG projects, and we identified 24 gaps at the PRCI, I would say, perimeter, so mainly transmission network. So for the final report, and I think as you were, the GERG was partner, I think you had a copy. We include an executive level, so it's a presentation of the key result and the gap. Expert level, more for experts, to have a summary of collected data, and at the end, all the raw data collected. We were able to identify top priority for PRCI and also list of possible partners to work on other gaps, and I will present to you the top priority. And also it enabled PRCI to create the Emerging Fuels Institute in August this year to coordinate all the R&D activities dedicated to emerging fuels. So it's not only dedicated to RNG, but it also includes hydrogen. I think you could go to the next slide about the top priority. So it's really in adequation also with the data collected. I told you that we collected a lot of data regarding RNG composition and the fact that we have a lack of I will say data on some point. So the first idea will be to create RNG trace component databases, or at least it was highlight like that we need to consolidate existing and new data on trace component. And this idea, will be to design these databases and see how it could be implemented and open to a PRCI member and also maybe associate member like and other R&D organizations. So we have to think about how we want to work on this topic. And the second topic, it's more related to analyzer. So we all have this dream that we want to have like a single, integrated unit to analyze, the main component that we have in RNG, but also some selected trace component. As I don't know for you today in your country, but at least in France, we need several analyzers to be able to analyze at least the main RNG component, and for the trace component, most of the time it's a spot control. But okay, it could be nice to have a single unit to do all these kind of things, but for that we need to find it or to develop it and then to evaluate it. And we also need to be sure that it's cover the need of the gas industry. So first of all, the first step will be to summarize the need and to begin a benchmark on the market. So it's the end of my presentation. I saw a couple of questions in the chat, so just give me 1 minute to answer to it. So there is a question of Robert. Okay, so you mentioned Store and Go project. Okay. Okay, it's for biogas industry. Okay, I didn't know this one, but thank you for sharing this information. I think we can take into account maybe in our as data.
Maybe I quickly explain this. So this is
Yeah.
The Store and Go project was originally a very interesting power to gas project. So looking at really utility level storage way beyond what batteries are able to do. They have a lot of very interesting papers in this subject where they really look at the feasible scaling up of power to gas to the levels that we would need for renewable energy. But what was very interesting is one of the technologies that they were using to upgrade sewage gas at the Solothurn site. So the sewage gas was rich in CO2, H2S, oxygen, everything that you don't want to have in your sales gas. And they found that this single-cell archaea microorganism not only is very robust and survives all these nasties when you expose them to it, but they thrive on it. And the output of this with the archaea and with a little bit of hydrogen on top of it was sales gas quality that could be put directly into the local distribution system without any caveat. And as I also gave a link to the American company Archaea company, who are doing now giant commercial projects with this technology, again upgrading landfill gas to sales gas quality. And I think that if we want to be serious with the biogas, it is probably better to find the technologies to upgrade the gas to sales gas quality than try to reduce sales gas specifications in order to allow us to feed the biogas in, especially if it is technically feasible, as this seems to show.
Yeah, totally. I agree with you about the fact that we need a really efficient upgrading process. So thank you. Thank you for sharing the information. I will have a look after this meeting. So to answer to Xavier's question, yes, you're right. The Emerging Fuel Institute has not really started yet, but it will start it soon. We received a couple of information just last week, and it means that R&D, also R&D project related to emerging fuel will be in this institute, which is part of PRCI. I don't know if I'm answering to your question, but it's the information that I have. And I also, Bettina raised his hand.
Yeah, thanks a lot. I want to comment on the Solothurn plant. So in the Solothurn plant, it was not sewage gas directly. It was a CO2 which was brought by pipeline and then together mixed with the hydrogen, and then the archaea made the methanation. But we have a second project in Switzerland, which is doing this biogas upgrading with archaea, also archaeas, but archaeas directly from the, how do you call it, sewer sludge? So they're like native ones. And this project is now in starting the commissioning. So the cold commissioning is started, and then I think they should go into production this spring. But I can put a link in, or you can contact me and I can give you more details about the project itself. But what is true is in the Solothurn plant, they could achieve with the archaea methanization with very limited upgrading, so just the sulfur removal, and then they could inject it directly into the grid. This was really easily done. So there were not a lot of nasty components, or the filtration was very limited after the methanation process.
Okay, thank you very much. It's really interesting to have all this information with a new project.
And thank you to you, Emily, for
thank you to and you to the GERG. And if you have any question, you can ask Robert, or you can email me. Thank you very much.
Yeah, and now we are a little bit short on time, so it's time for coffee break. Now we have 2 presentations on LNG, bio-LNG, and Svetlana, are you ready to present?
Hi, yes, good morning, Torben and Alexandra. I'm ready. So yeah,
Please,
first of all,
go ahead.
thanks a lot for the invitation, for the opportunity to participate in this conference. So my name is Svetlana. I work as a key account manager for Fluxys Belgium. Just checking that you hear me correctly, yes?
Yes.
Okay, good. So yeah, I work as a key account manager for Fluxys Belgium, and today I want to introduce a little bit the bio-LNG service that we offer at the Zeebrugge LNG terminal. So maybe could you switch to the next slide? Maybe to begin with a few words about Fluxys. We are a gas transport infrastructure company. We own and operate the transport infrastructure in Belgium, but also the storage facility in Loonhout and the Zeebrugge LNG terminal. As a group, Fluxys is active in a wide range of European countries. And for instance, we also operate the Dunkirk LNG terminal in France. Next slide, please. A bit more about the relevance of the topics that we are touching upon today. For us, really, for the group, being the transporter of future energy carriers is a core pillar in our strategy. We work a lot on biomethane initiatives, on injection of biomethane into the Belgian gas grid. That's also a topic for later today, I believe. And we also invest in hydrogen and CO2 transport infrastructure, especially in Belgium, and participate in a wide range of H2 projects. But today I wanted to speak about the bio-LNG service in Zeebrugge. So maybe next slide again. Just a few words about why we wanted to develop this service. We really see exponential growth for small-scale activity at the terminal. So there are a lot of bunkering operations in the region, growing truck loading activity for heavy-duty transport, etc. And with the available technologies that we already have, and in the framework of the current regulations, Fluxys has tried to develop a product, a service that enables our client to meet EU sustainability criteria for their biofuel targets. So as you can see, that's a nice picture of the Zeebrugge terminal. And the terminal is ICC certified since December 2020. So the ICC is the International Sustainability and Carbon Certification. And basically this certification enables us and our bio-LNG service to be compliant with the RED II directive, so European Renewable Energy Directive. The 2 services that we are offering, so maybe also next slide, is first of all the possibility to bring bio-LNG, a cargo with bio-LNG and the associated ICC bio-LNG certificate to the terminal. Then you can store this bio-LNG in our storage tank. We have 560,000 cubic meters of storage space. And then you can use this bio-LNG for different applications, for transport, for end users, for bunkering activity, etc. And the second service that we offer, and that is maybe a little bit more creative, is to bring the biomethane from the biomethane production plant, inject it into the transport network, and with the backhaul service, you can bring this biomethane from the grid to the bio-LNG, to the LNG terminal, where it's liquefied, and with the associated certificates, you can store this bio-LNG and use it for different applications again. So the way that this liquefaction works and is possible is that we have 2 recondensers in the terminal that are used in the process flow for regas. So the recondensers, in them, the natural gas is cooled down and liquefied, and the physical liquefaction process is what allows us to convert the biomethane certificates into bio-LNG certificates. And once it's liquefied, as I was mentioning, basically, you can use it for different applications, again, truck loading, industry, bunkering, etc., etc. And both of these processes are compliant with the ICC. So, okay, we have those 2 services, and maybe also next slide. We see growing exponential growth for the small-scale LNG activity and growing interest for the bio-LNG service, especially for the transport sector. We have developed the service with the technology that is already existing, with the certifications that are in place. But the main takeaway maybe I wanted to give today is to say that there are still some constraints on the recognition of the process and the certificates between different countries. And we see that in countries such as Germany, where there are a lot of incentives to switch to low carbon fuels, there are still some burdens, administrative burdens, regulatory burdens on the recognition of this process, even though it's ICC certified. So I really hope to see in the future, and also for new technologies and new processes that are being developed, a harmonized recognition of them. And yeah, that's really the point I wanted to make today, is that we already have some ways to reduce GHG emissions, etc., but the acceptability between countries is really a blocking factor today. And yeah, that was really a brief, short, maybe next slide, introduction. But if you have any questions about the services or want to discuss with us how, we are already in discussion with other national authorities, but if you have any ideas, support, information on this topic, we'll be happy to discuss this with you. Thank you very much for your attention.
Thank you very much for your presentation.
Sure.
And there are questions, I see.
Yes, thank you, Svetlana. Just a question to be sure I understood. Do you have currently a liquefaction system at Zeebrugge, or is it a project? Is it already operated?
Thank you for your question. So yes, yes, we do have 2 recondensers at the terminal that we use to liquefy the boil-off gas. And this reliquefaction of the boil-off is accepted by the ICC as bio-LNG liquefaction process. Yes,
it's very interesting. Okay, yes. And just to be, if it is not restricted information, what is the capacity of the liquefaction enabled by the recondenser?
Yeah, the capacity, it depends, of course, on the activity of the terminal, but firm, like the minimum send out that we require, we have 21.6 gigawatt hour per hour, yeah, of capacity. That is the minimum. And then the rest depends on the activity at the terminal.
Okay, thank you.
Maybe.
Yeah.
I see some raised hands.
Yeah, okay. I raised my hand, so I start speaking. It's a very interesting presentation, thanks. It's an interesting concept to inject biomethane and liquefy it and then transfer it to bio-LNG. But I assume, what's the use of it? I mean, there must be a financial incentive. Can you elaborate on that?
Yeah, financial incentives. Well, There are some countries where we have, well, not we, but our clients have already exported this bio-LNG, and where basically there are very high carbon taxes on transport fuels that do not apply to the bio-LNG. So when you look at current natural gas prices versus biomethane, bio-LNG prices, plus the carbon tax added to the natural gas price, you can see that the difference is not that big anymore. So I guess that's part of the incentive for clients to switch to biofuels. Hope that replies to your question.
Okay, thank you.
Okay, thank you. And I think it's time to go to the next presentation.
Sure. Thank you so much.
Thank you. Laurent, will you enlighten us on some technology? You're muted.
Sorry, thank you very much. So yes, it's my turn to give you an overview of liquefaction technology. So it is an excellent transition with the former talk's speech of from Svetlana. So my name is Laurent Benoit. I work at ENGIE lab and on liquefaction precisely. So first, can I take? Yes, good. So as a starter, what do we mean by bio-LNG exactly? So the acronym bio-LNG stands for bioliquid natural gas. And behind this definition, there is actually two types of bio-LNG that can be met. The first type is more obvious. It deals with direct treatment and liquefaction of biogas, of a biogas plant. And in the end, we will talk about it later, but almost only methane is remaining in the final stream, liquid stream. So often liquid biomethane is synonymous of bio-LNG. Or to say it in another way, LBM is a kind of bio-LNG and the most often type of bio-LNG met. But also, you can imagine a different way to produce bio-LNG, which is already made, we will see. It deals with liquefaction from the grid, and somewhere on this grid, some biomethane has been injected. So if you buy certificate, if you buy a guarantee of origin of your green gas, your grid gas liquefied can be considered as bio-LNG. So this is the two main types of biogas, of bio-LNG, sorry. So why liquefying? Very simple answer is simply to help to ease the handling of biogas or any gas actually. And to be even more precise, the goal is to reduce the volume of storage. So typically, if you consider the equivalent, the volume equivalent of a full swimming pool of biogas, this volume, with this mass of biogas can be reduced in volume at the equivalent of 2 bathrooms. So it's a huge reduction of the footprint, and this is the main interest of the liquefaction. And to do this, we mainly use the cooling. So even if it's not, it's possible to store at higher pressure than 0 bar gauge or 1 absolute bar. It's currently the most often kind of storage for bio-LNG is still 1 bar. So it means that it is stored at a temperature of equilibrium equivalent to minus 160 degrees Celsius. So bio-LNG needs cryogenics. And once you get your liquid biomethane, biogas, what can we do with this bio-LNG? Which market which markets can be addressed, and which kind of application. So the first application is, which I started to explain. Imagine several plant, biogas plant and a biomethane injection plant connected to the grid. So they inject their production into the grid, and somewhere elsewhere on the grid you can liquefy the equivalent quantity. So you can produce by this way a bio-LNG if you buy again the certificate of guarantee. So the advantage of this strategy is that you are not anymore constrained by the biogas, the biological feedstock logistic. You can liquefy as much as you can, provided you are able to buy enough certificate. So it's technically it's a big advantage, but the drawback is the regulatory recognition. So it's a bit like, not exactly, but probably similar to what Svetlana mentioned earlier. And of course, you need to be, on the financial point of view, you have to be able to buy enough certificate. The second, I would say the second type of bio-LNG chain we can meet, it's the most obvious one. It's, let's assume a biogas plant remote from the grid gas, so not connected to the grid gas, let's say at 20-30 kilometers from the grid gas. Then you can use liquefaction to either inject it after transportation. So you liquefy at the biogas plant after treatment. You put your liquid biomethane into a transport truck, and you can inject it remotely. Or you can also sell it directly to a fuel station or retail LNG station. It exists almost hundreds already all over Europe. So it's another possibility. And most of the time, I would say that it's this last one, the direct biofuel production, is more promoted lately, because on the thermodynamic point of view, you keep the cold liquid until the end of until the end customer. While with virtual pipe, it's absolutely possible, but of course you need to vaporize it again, so you lost a part of the energy spent to liquefy. But anyway, both are totally making sense, and it depends on the business case. The last application, which is more specific, and it's an innovation from ENGIE, I think. It's a kind of adaptation of the old concept of peak shaving, because in some situation locally on the grid, most of the time the grid consumption in France at least is driven by heating needs. So during summer the consumption is falling, and if you have too much injection plant connected to the grid, they cannot during summer always inject all their production. So in order to not waste this biogas, we can imagine, and it is already applied today, a small peak shaving adapted to the liquefaction of this other seasonal overproduction, let's say 2 weeks, 3 weeks, 1 month of production stored locally and under liquid form and rejected later. So this is the last, I would say, possibility of bio-LNG chain. So practically, when we talk about bio-LNG today, how much application, how much plants are existing? So by 2021, I would say a dozen, maybe 14 at maximum. So it's, of course, it's very few. It's an industry at birth when you compare with more than 600 injection plants in Europe. It's of course a very small amount, but it's an activity in a strong development. Also, it's very European activity so far. Most of the applications are built in Europe currently. And if you look at the type of application, today it's more for biofuel production. There are already 2 virtual pipe application, one in Northern Ireland, in Ulster, Greenville, and the second one in France, Métabray. So they liquefy, transport, and reject, or use it anyway on the grid. There is also one grid gas liquefaction with buying of a certificate. It's a project currently built by Shell in Germany at Godorf. So it's much bigger feed rate, as you can see. And also there is a small peak shaving application in France at Plainval, which started 2 months ago. So it's very... And I would say also very important, we can see now the takeoff of the industry, because it's not new bio-LNG. It's the first bio-LNG plant operated was maybe in 1997 in Albury in UK. But during 15 years, it was mostly pilot plant, proof of concept, not very commercial plant. Now we can see real commercial plant run, not just pilot or innovation. So it's really now the takeoff of this field of activity, in my opinion. So if you compare now liquid biomethane against LNG, standard LNG, and I would say also LBM liquefaction plant versus a standard large-scale liquefaction plants. What can we see as a difference and a common point? So if you look at the production chain of the production process, starting with the feed gas step, at the inlet, one of the most striking difference is the pressure at the inlet of the LBM plant. It's only 1 bar absolute, and it's a big difference for the process, because in standard LNG, still since the feed gas is coming from underground fossil origin, you can take advantage of high pressure, and of course for a liquefaction process, which is a cooling process, when you need to cool to liquefy a gas, the higher pressure it is, the warmer boiling temperature is, and then the cooling duty is smaller and the efficiency of the process is higher. So it's easier to liquefy at high pressure than low pressure. So to not take advantage of this high pressure is a difficulty, and has to be overcome by using more compressors. Second point, obvious, but it's good to have order of magnitude in mind. LBM plant is maybe 500 times or 1,000 times smaller than a normal large-scale liquefaction plant. So there is a scale effect totally different. So technical economics are very different, of course. Talking about feed gas and purification stage, the content, of course, of feed gas in a LBM plant is very different from a large-scale plant. Not very different, but basically much more CO2 content in the biogas than usual fossil gas. Even you can meet always very sour gas in fossil activity. And another point which is very important is the efficiency of compressor, because at small scale, at small, I would say a compressor of few hundreds kilowatt of power, it's not a question of adiabatic or polytropic efficiency, it's a question of staging. And there is almost a poor or no intercooling between 2 stages of compression. And in the end, you spend much more energy to compress with small compressor, the equivalent of the same stream, than with a large compressor at larger scale. And as the final point, the storage, the final product is a little bit different. So far, I said many drawbacks, many difficulties to face with bio-LNG liquefaction. Here there is an advantage at small scale when taking into account the production. You need to store the bio-LNG content. You need 20 or 40 cubic meters storage, so it's not big. And at this size, the type of pressure storage can handle much higher pressure, typically 14 bar gauge easily. And so it is an advantage, but it is not used so far because when you need to blend bio-LNG with standard LNG, which is at equilibrium pressure of 1 bar, of course, if you don't want to vaporize too much your bio-LNG, you have to liquefy into cooling down your bio-LNG until 1 bar pressure of equilibrium. But you could, actually, my point is, from the technical point of view, it could be possible if we don't blend the two LNG standard and bio-LNG, you could store and have a logistics of bio-LNG at a higher pressure, which could save money because it's easier. In the end, we talked about earlier about O2 content and nitrogen content. Of course, O2 and nitrogen, oxygen and nitrogen are more volatile components than methane. So if you don't do anything, you will keep them until the final liquefaction, so into your storage. So it's an issue to. And just a remark, an additional advantage of bio-LNG, it's almost pure methane. So sometimes for methane number issues, for instance, or even for specific application, for instance, rocket propellant, they very enjoy stable composition, and more people are considering methane, liquid methane as a potential fuel for rockets. It's an advantage to have such a very stable composition. And also in this comparison, just order of magnitude to keep in mind, finally, the process of liquefaction of LBM is almost twice more energetically intense than the equivalent process at large scale, because mainly of the pressure inlet biogas low and the size of the plant, which does not allow very good compressor energetically. So now let's go deeper in the discussion and the technical features. Often when we talk about liquefaction, people think only on cryogenics. They say they focus their attention on the liquefaction and cooling process, but a bio-LNG plant is much more aspects than only the cooling and refrigeration system. I would say if I can compare the bio-LNG plant with Formula One car. In Formula One car, the equivalent of engine would be the cooling process. So it's important, but if you want to win the championship, you have to have a good aerodynamics and you have at least good pneumatics or road holding. And the equivalent of, I would say, aerodynamics in our system, it is purification, because purification process has a big and important part. And also the feed gas management is a very important aspect. So on the left, you can see a sketch of a typical biogas liquefaction plant. So if you start from the beginning with the feed gas, so you take feed gas at 1 bar, it's almost with almost 35% molar content of CO2. It's about 30 degrees of temperature. You compress it. So you compress this gas either to beat pressure drop, but also, as I said, it's better. The higher pressure it is better. It is the smaller cooling cycle you need. Second, high pressure can help to separate, to purify the biogas. So it's I mean, there are different strategies of compression. Of course, the more you compress, the more expensive it is for the compressor. So there is a trade-off to find. So feed gas management is, on this first part, is very important in a liquefaction process. Still in this feed gas management, keep in mind that you have to store at a pressure which is not necessarily the pressure of a compression. So as I said, so far we store at 1 bar. So in the end, there will be necessarily an expansion. And depending how you handle this expansion, typically depending how low you cool down your bio-LNG, you will handle different end flash gas, that is to say, vaporization, final vaporization. And so again, there are several strategies. You can, for instance, let's imagine you compress your biogas at 40 bars. You purify it, okay? You have methane. And at 40 bars, you can liquefy methane at only minus 80 degrees. But if you expand it immediately, you have a liquid part at minus 161 bars, but also a part of vapor, a huge part, let's say 50% of vapor produced. So you have to handle this. If you don't cool down too low, you have to handle lots of vapor. If you cool down much lower, you have not much vapor, but you have a bigger cooling cycle. So this is in this way, feed gas management has to be thought. About purification process, it's a very important point. The more striking aspect is, of course, you need to purify biogas and upgrade it like in any, I would say, bio-injection plant with the same technologies, membrane, amine, water scrubbing, adsorption on molecular sieves. But in addition, with liquefaction, you have to drastically reduce the amount of water and CO2 because to avoid crystallization into the heat exchange line during the cooling process. So typically you have to reduce the amount of CO2 at a content lower than 50 ppm. So it's 1,000 times lower than the standard grid specification. And to do this, the traditional way, so we call this last step polishing. And this polishing, currently, there is not many technologies. The most used is molecular sieves. But in the framework of bioenergy industry, there is another way, which is called cryogenic purification. So some providers said, okay, crystallization, we can handle it. Crystallization, it means you have a deposit in your heat exchanger. So if you are capable to master this rate of deposit, you have a way to separate CO2 and methane, and you neutralize cooling and separation. So it's more complicated, but potentially it's a gain in terms of equipment. And so there is currently a solution commercially operated successfully using this way. Talking about cooling process, with LBM and bioenergy liquefaction, you can find 4 types of liquefaction process. The most obvious one is open loop with nitrogen liquid. It is only used for small capacity and temporarily use, not often. The main other way are refrigerant with phase change. It is often used with mixing component. That's why we call it mixing refrigerant. It's the most efficient way, but it is the most complex to harness, to master, and less flexible way. A more flexible way, but less efficient, is to use pure gaseous refrigerant. We call this reverse Brayton cycle. Actually, in such a cycle, the cold is produced by expansion of a cold gas. So it is the reverse of compression. You know, when you compress a gas, you heat it. So when you do the reverse, when you expand a gas, you cool it. So we use this kind of effect as a refrigeration loop. And very similar on the theoretical point cycle, which is Stirling cycle, but practically it's very different because in Stirling cycle it is also vapor gaseous refrigerant, but the expansion and the cooling are made at the same time. It requires small volume to treat, so it's good for small capacities, but not for big one. And if you look at, I would say, now we can illustrate this typical description of bio-LNG liquefaction on some existing bio-LNG solutions. So here it's just an example. It's not the full list of existing solution, but just to illustrate this way of discretize, I would say, the bio-LNG process. So for instance, Wärtsilä is typically proposing solution with change phase change refrigerant, MR cycle. Also, I mentioned the so-called cryogenic purification. It is proposed by Cryopure, so it is operated on 2 plants already successfully. But as you can see, they use a mixing refrigerant cycle for cooling, but they could use any type of refrigerant cycle with their cryogenic purification system. Also, I mentioned, yes, a very interesting also process is LICAL system, which actually compress the biogas, the feed gas, at almost 120 bars, so very high compression. And at this, thanks to this high compression rate, they only cool down until -70, -80 degrees. So it's almost not cryogenic temperature. And after they have a liquid stream, but also a big creation of vapor, but it's not a problem. They say that the gain on the cycle, refrigeration cooling cycle, is balanced by the quantity of gas of vapor to treat. So you see, there are many. What is very interesting in bio-LNG liquefaction, it's a very beautiful playground for engineers because you have many more solutions existing than in the standard LNG field. Just to conclude, some figures about cost, because it's often it's a very often question asked. So typically, these are some order of magnitude from our data internals. Today, I would say that a typical biogas plant with producing, for instance, 400 normal cubic meters, which is, I would say, the average in Europe. So it means that if you want to liquefy, you can find a solution which costs, I would say, between 25 and 30 euros per megawatt hour. So it's typical, the most optimistic price, but realistic. And if you double the production, there is a huge scale effect because, for instance, if you double this production, it costs 30% less typically. Also, what we saw, it's a good, very interesting trend. The past 6 years, the cost almost fall by 20%, even 30%. Mainly because there are more solutions, more technical providers, and also because the field of activity is beginning more mature. So to conclude, what are the next technical challenges that we can foresee? I think on the technical point of view, the polishing stage, that is to say the final purification to minimize the CO2 content at 50 ppmv, it's not yet, I think there are still room to improve the process because it's not yet achieved. There is no as strong development as with membrane or water scrubbing development. So there is room for new development, and at NG Lab we have a polishing test rig currently operated to improve these aspects. The second point is the standardization, the improvement of the standardization of the liquefaction technology. Here I am talking about the series effect, which is not seen because there are only a few number of liquefaction plants. So if you compare, for instance, with membrane cost with the last 10 years, when the number of injection plant has exploded, the cost has decreased strongly because of a series effect. So we can see this, I think, also with liquefaction if the development is kept. And the last very point important, I beginning to talk about it, it's the pressure storage optimization issue. I said that we could store at higher pressure. This higher pressure storage could enable to reduce the cost of bioenergy treatment by almost 20% with existing technology, but we don't do this because we want to blend, we want to use the same infrastructure than standard LNG, retail LNG. If we separate these two logistic chain, we could easily gain in terms of price, but of course it's more constrained for the market. So thank you for your attention, and questions are welcome here or later by email. So thank you, everybody.
Thank you very much. Thank you for a very interesting presentation. And a lot of clapping hands, I see. That's good. Is there also raised hands?
Yes. So question from yes, the question about oxygen. True. You can at the end of a process of liquefaction, actually you could separate oxygen and nitrogen due to the final end flash. You could recycle it into the digester. So it's possible. Definitely it's possible, but sometimes we don't like to connect too much the two processes so far. But I think in the future it will be a way to recycle oxygen and nitrogen and to not keep this oxygen into a final bio-LNG or LBM. It's definitely a way, yes.
Maybe from my side, from the standardization activities, did you already use the standards which are produced by STEN for the specification of the bio-LNG and for injection into the grid or use it for automotive fuel? And the same question is also for Svetlana.
Sorry, can you repeat? I didn't hear it correctly.
Did you already make use of the existing standards which are produced by SEN for the specifications of the gas specification?
Well, so far I didn't see any problem on this point for BioLNG application. So I don't know if Svetlana has more insight about this.
Oh, that's at least a good answer. That's good news if you don't see a problem.
So, okay, another question from Bettina. Yes, how we can handle so far the injection to the grid in France with pure methane. The grid specification has been met even with pure methane, but it's true, it depends very strongly of your local regulation. If you think that it's too much methane content, we could still keep 1% of or 0.8% of nitrogen. So it's still possible to play on this final fine tuning, I would say, composition. But so this is a way to reduce slightly the amount of CH4. But so far, in the virtual pipe, for example, in Metabre, I didn't heard any problems of grid gas specification meeting. But again, it's true, it depends strongly of your local local specification grid.
We have time for another question if someone has a question. That doesn't seem to be the case. Thank you very much for your presentation, Long.
Thank you.
And that leads us to the final part of this this session. We have a panel discussion here where the title is lifting obstacles to increase the amount of biomethane injection. And for that we have 4 panelists who will tell us more at their point of view on this issue. Erik Bødker, which has been on the scene already, he's chair of the TC408, which is the technical committee for standardization. And Annette Møller Hansen, she's a project manager at the Danish Gas Technology Center and have been participated in some of the SEN biomethane work on oxygen, for instance. Next one is Erik Pohlmann, who is a senior consultant in the gas measurement at Kiva, and Erik has a lot of experience in gas quality and standardization as well. And the last in the panel is Antonio Gomez-Brac. Antonio, he's co-chair of the GERG PC on distribution, utilization, transmission and storage. And beside that is the head of the section of Energas transport, where this team provide support on hydrogen, biomethane, methane emissions, and so on for the whole Energas group. Erik, will you open the session with a presentation?
Yes, thank you very much. First of all, thanks for the invitation, and also congratulations with the 60th anniversary of GERG. I think it is very important to have that European Research Institute available, which is helping to take away the disadvantages or the problems we are facing in introducing biomethane into the grid. I have a lot of slides, but most of them are already explained by Marine, so I can go through it very quickly. But it gives I will give the framework of SEN, how it is working inside SEN, I think this picture is always fun to see why we are using biogas and why we need to use biomethane. Also, for my background, I'm working at Total Energies and focusing on the use of biomethane as automotive fuel, but also in B2B activities in industrial applications. A little bit about the background of TC408, and I think that's also very important to understand that the group who is active for biomethane, PC408, is very closely working together with the CEN-TC234, which is focusing on normally distributed gas, fossil distributed gas. So a lot of the specifications which are in the biomethane are directly referred to CEN-TC234. And that is also the way how we set up these standards. There are two standards published: the specifications for biomethane for injection into the grid, and the standard for the use as automotive fuel. And we have published a technical report about the health criteria elements of the trace elements in biomethane. I will come back to that later. So to specify the scope of PC408 is mainly if you have your biogas, your upgrading facility, then part 1 is describing the injection into the grid, and then you can use it as for household applications, for industrial applications. But if you want to use it as automotive fuel, there is a second part which is describing the specification as automotive fuel. Also, we also specified non-grid source natural gas, and that's, for example, when you're talking about bio-LNG. And you can use bio-LNG for injection into the grid, or you can use it as an automotive fuel. So that is defining the scope of the standard. And here you see all the elements we are describing in the standard. All the elements which are described in blue are defined by the other standard. All the elements defined in green are described by the CEN-TC408 and specific for biomethane. The same for the automotive fuel specification. So the hydrogen sulfide, hydrogen dew point, hydrocarbon dew point, methane number are standard specifications for natural gas. The green elements are the elements which are described for the biomethane as used as automotive fuel. I think the presentation will be shared, so you can have a look at it later. And the technical report is the limit values for based on health criteria assessment. So if you ignite your stove and you have biomethane in the natural gas, how much of those components can be in the biomethane before it have a health effect? And those limit values are very, very low, and there are no obstacles for that. The reason that it is a technical report, it's all based on studies and different models which were used. And that's the reason to at least describe the way how it was determined. The new activities of the TC is also working closely together with ISO TC193. Because when we set up all those specifications, we figured out that not all measurement methods were available and standardized. So we are working closely together with ISO 193, who is setting up those analysis methods. And of course, the research project, which was clearly explained by Marine, the previous research on siloxanes, the reports which was published in 2013, it was basically a Dutch research on the effect on boilers. That is now extended, that research, in the GERG research project. And the result of that research will be used in the revision of the standards. The same for siloxanes in biomethane and the effect on engine performance. The research, this report was published in 2016. Now we are doing the research again for also heavy-duty engines, and that's also performed in this GERG project. So yeah, the same slides are already presented, trace components and the potential impacts on European gas industry. And this is the project which is currently going on and which will be used for the revision of the standards of the 16723 part 1 and part 2. So that is, I think, the short introduction of the 10 TC activities.
Thank you very much.
Okay.
And we will take the questions when all the presenters have presented what they like to present. So I think we would continue to Annette. Are you ready to present?
Yeah. I'm sharing the slides myself, or someone else?
I will bring them up again. Apologies for that. Just 1 minute.
One more time. Sorry, my sound was off. I'm sharing the slides myself.
I can just let me find the right one. There we are.
Thank you. So I'll just talk briefly about biomethane and the production of it. If you can just change the slides to the next one. This looks weird when you haven't. But just briefly, the entire production chain of biomethane. You have the biomass or manure and such, and then you do a bacterial digestion of it to produce the biogas, which is only 60% methane. So you have to upgrade it somehow before injecting it in the grid. So you do some pre-treatment if necessary, but there's this upgrading process where you remove most of the CO2. So you have 98% or more methane before injecting it. There are some relevant issues when doing that. I've just highlighted a few from a Danish perspective that we work with. There's both the oxygen that's already been mentioned, where fossil natural gas doesn't have any oxygen, but when you produce biomethane, it often has a higher oxygen content, which can cause these worries of corrosion and bacterial growth and sulfur depositions and such. Then there's the methane loss. Sometimes you lose some of your... Can everyone see the slides? I can see there's a question in the chat. So it's just
yes.
you.
We see the slide.
Okay, then I'll just continue. I don't know why someone can't. Some of the methane can be lost together with the CO2 stream, and that's of course bad from a global warming perspective, but it's also bad from an economic perspective because it's a sellable product that you just lose that way. So you want to keep that as low as possible. Then there's the CO2 purity. These days we'll talk of CO2 capture and for either storage or together with power to X to produce methanol and otherwise. It's interesting to produce the CO2 as pure as possible. And then, of course, is the price, because you want this biomethane production to be competitive compared to other green energy sources. So those are important factors to look at, and they depend on the upgrading technology that you choose. So I'll just briefly go through those and how they relate to these focus points. Next slide, please. So the water scrubber is a good and well-known technology where you have the biogas, compress it a bit, and then you wash it with water to remove the CO2. And then in order to regenerate that water, you flush it with air to drag out the CO2, which means that the CO2 will be heavily diluted with air. It will also contain a substantial amount of methane that was also absorbed in the water. And because you regenerate it this way with air, the recycled water will be saturated with air, and that means that some of that air will go into the biomethane. So when you upgrade your biogas this way, the biomethane will naturally have a content of air, meaning oxygen. Next slide, please. The amine scrubber is relatively similar. Here you wash the biogas with an amine that also removes the CO2, but in this process you regenerate the amine with heat, where you boil off the CO2, meaning that the CO2 will be very pure and there's very low methane loss. And since you don't add any air, you have the potential to produce the biomethane with virtually no oxygen in it. The drawback of this process is that it's quite heat intensive, so in order to make it economically feasible, you have to be able to recover that heat and reuse it somewhere else. Next slide, please. Then there's the membrane process. A membrane is sort of like a sieve, so the CO2 can move through it while the methane is kept retained. So you normally do that in a series of steps, where you first have your biogas through one membrane, where you produce a more methane-rich stream, which is not ready for injection yet, and then you have a second step to produce the biomethane and recycle the more CO2-rich stream, and in the same way you have a second stream for the CO2-rich stream, so you produce CO2 that's relatively pure and again recycle. We have these recycles to keep the methane loss as low as possible, but there's some methane lost with the CO2. But you produce a quite pure CO2 stream, and the biomethane has the potential to be very close to oxygen-free if possible. Next slide, please. And then there's the PSA process. And disclaimer, I know very little of this because we have no PSA processes in Denmark, but I included it since I know that it's much more used in the rest of Europe. But the overall idea is that you compress the biogas, and then you have these beds that contain material where the CO2 is adsorbed on the surface. So you lead the biogas through, the CO2 is adsorbed on the surface, and you produce the biomethane. And at some point, this material is filled up with CO2. You need to recover it. So you lower the pressure to remove the CO2. So in this way, you don't add air. So I assume that you should be able to produce biomethane with very low oxygen content. But the methane loss, as I've understood it, is quite high, which might also influence the CO2 purity. Next slide, please. And then just a table to summarize what I've said here. So with oxygen content, you can produce it with very low oxygen content from the amine. And you should also be able to do that with the membrane and PSA process if you avoid adding oxygen in the earlier parts of the biogas process, while the water scrubber is unable to produce with lower than 0.2, 0.3% of oxygen. So if you want to avoid adding oxygen to your gas grid, you need to do some catalytic removal, which will of course be an extra expense. For the methane loss, the amine scrubber has a very low methane loss, and the membrane is also in the lower-ish end, while the water scrubber and PSA have quite high methane losses. And in Denmark, this means that many water scrubbers have started having RTOs installed on the CO2 stream. That's thermal oxidation or combustion of the remaining methane. So that solve the global warming issues, but of course you still lose your product. For the CO2 purity, again, the amine scrubber has a high purity, and the membrane and PSA should also be able to produce high purity CO2, while the water scrubber is diluted heavily with air. Then DGC did a study a few years ago about the expenses for this upgrading process and sulfur removal isolated. And it's around 6 to 10 euro cent per cubic meter of methane to produce, to do this upgrading process, make it ready for grid injection. And then the common question when I say these prices is how much is that compared to the general price of producing biomethane, the entire production chain. So if you could just change the slide, please. So here we have plotted the total expense of producing the biomethane all the way from getting the biomass and including grid injection. So we can see that's around 60 to 80 euro cent per cubic meter of methane. So it's around 10% of that price that goes to the upgrading cost. And an interesting fact from this graph is also that there's a lot of economy of scale, meaning that in Denmark, we see that most newer plants are quite big in size because it's just cheaper to produce the biomethane with a bigger plant. And just the last slide. I've also included this, and I'll not go into details with it, but it's just looking at the different expenses for both the entire production of biomethane and only looking at the upgrading. So what we can see from the left graph is that this upgrading is around 10% of the total cost of producing biomethane. And a recent study showed that we should be able to optimize this process to save 10 to 18% of the production expenses. And for the upgrading process, the best way to lower cost is to choose an effective and cheap way of sulfur cleaning and to have a high degree of reuse of this heat if you have an amine scrubber. And of course to keep the plant running as much as possible because it's just expensive to have it not running. Yes, that was it from my part.
Thank you very much, Annette. And yeah, Erik, will you take over from here?
Okay. Okay, thanks for the previous presenter. A lot of clapping hands. Well, first of all, I would like to join Erik. He's, in fact, he has the same name as I and is a former colleague. And also, I would like to congratulate the GERG with the 60 years anniversary. They must have been established during my lifetime, but I was not conscious of that by that time. My first experience with the GERG was in 1989 when I joined a meeting at Gas de France on materials, and I was very impressed by the facilities and the laboratories they had by that time, and I think still have. Well, my talk is about standardization in gas quality. I would also like to give some feed for a discussion, in fact, because this is a panel discussion. And I've only a few slides, but I would like to express that regulation is a mean. It's not a target or a goal. It's a mean to have a good quality of the gas. And it's the way how we as people deal with regulation. That depends the final gas quality, because only a regulation is not an achievement for a good gas quality. First of all, I would like to give some insight on the way the regulations are in the Netherlands. So if you can give me the next slide. And the biomethane production in Holland is growing. By this time, we have about 60 injection plants and a yearly volume of 200 million cubic meters a year. It's varying from very small, let's say 20 cubic meters an hour, I said a year, but that's a mistake I made. It's 20 cubic meter an hour, up to very big plants of 4,000 cubic meters an hour. Most of the injection plants are injecting into the distribution grid that has a pressure of maximum 8 bars, but can also be lower depending on the location. And 2 of them are injecting in the transport grid of the 40 bar grid. The quality parameters for the transport grid are more severe, especially on the oxygen content and the water dew point. The situation in the Netherlands is that you can inject as long as there is availability in the grid, and the availability is limited by the minimum offtake, and that is during summertime, especially during summertime nights. Then you have the minimum capacity and the minimum offtake in the grid, and that depends on the possibilities of the injection. And on forehand, there's an investigation whether there is space in the grid. The consequence is that at some times, customers can meet 100% biomethane. So that means that the quality parameters have to be met anytime. So in order for safety, there's no forgiveness. You can't. There's no room for any margin in the gas quality parameters because some clients can meet 100% biomethane. In the Netherlands, I have been part of the SEN group that has created the standard EN 16723 part 1 for injection in the grid. But in the Netherlands, we have another standard. That's a governmental decree. And at some points, it deviates from the European standard, especially on silicon. Silicon standard, the specification is 0.1 milligram per cubic meter. That's quite severe, but in practice, it can be met. We have a deviating gas quality from most European countries because we have low calorific gas, and that's the limit is the margin is very small. It's between 43.46 and 44.41. So the margin for varying the quality is small. It's a small band, but in practice it can be met. And there is also a cap on the carbon dioxide because carbon dioxide can induce flame lift-off. And for that reason, there's also the flame index formula applicable. So that means in practice that if you have 100% methane, the 1B number is too high. So you have to add some inerts like carbon dioxide, but not too much carbon dioxide. So in most cases, you also add some nitrogen, which is already available in the process. And further, there's a declaration in the governmental decree that the gas may not contain contaminants that influence the smell. If you have the next slide, please. Well, I haven't said that the grids, the biogas producer is responsible for the gas quality, and it is delivered at an entrance point to the grid owner. And the grid owner has nothing to do with the manufacturer of the gas and has nothing to do with the purification of the gas. So that means that in that position, that's a difficult position, of course, for the grid owner. In order to overcome any problems, there is some additional procedures in order to guarantee a good quality control. I would like to outline those. First of all, there is an assessment before starting up, assessment on all the procedures producer has to meet. That means that he has to have a handbook with how does he calibrate his gas chromatograph, etc. How is the software of the quality control? There has to put in some alarm levels, how many times he measures the gas. In fact, he has to supply data every minute. And all those data are also transferred immediately to the grid owner. So the grid owner always have a look at the real quality parameters. And all main components are measured instantaneously. Upon startup, first the producer has to do a proof that he can supply good gas quality. It is done by a real startup of 24 hours. The gas is not injected but is flared, and then the quality is measured. If that is good, then the gas can be approved for injection, and upon injection there's a control of an external party like HEWA or like DNV that monitors the gas for 30 minutes with their own gas quality mobile gas quality apparatus. And well, our experience is in the first 30 days there can be some issues in the control of the WAB number and also on the control of the authorization equipment, but during those 30 days the quality is improved, and I think after those 30 days you can say that the quality is acceptable. But that's also an additional thing that is done in order to assure quality. Further, by law, one should have a quality control of gas samples every 6 months on all the trace components. And furthermore, additionally, on cost of the grid owners, there is a control on the odorant level and on the smell every month, because there are a lot of issues on odorization and smell. That's, I think, the most critical issue on biomethane injection. And I would like to add some things on, especially on the smell and the way people can act on that. And that's the next and the last slide. If you can give that, yes. Well, on smell, there are some critical components. As you all know, terpenes that are present in biomass, like in leaves, especially in autumn time when all the leaves are collected from the streets and put in the biomass digester. Some terpenes can be in the biogas. Butanone is one of the components that also can influence smell, as well as H2S. But due to well, in the beginning we had quite some issues on smell, but it has decreased significantly, and that is due to some measures. Well, the first measure is, I think, that you shouldn't accept that the gas is out of smell. And you have to be quite strict in that. For example, if it occurs 1 or 2 times after another that the smell is not well, it can be that the grid owner says, okay, you are shut off from the grid. And that costs a lot of money, because it's very costly for the producer to not inject the grid and to flare it off. But if it's necessary, it has to be done. And it turns out in practice that there is always a measure to control the smell issues. It can be done by strict input on the biomass, because some biomass gives more problems than others. And there are also ways to control it. For example, there are producers that have a special terpene analyzers based on spectrometers. Those analyzers are placed after the coal bed, and if you have an increase in terpenes or in acetone or butanone, those analyzers can register that, and then you can switch timely your coal bed to if you have mostly you have a dual coal bed in the installation, then you can switch to the other one. And in the past, it happens that the coal bed was saturated, and that it has been noticed by us that the smell is not well, and then they say, okay, oh, I will switch my coal bed, but you have to switch your bed, of course, in advance, and not when the damage has been made, of course. And furthermore, I think the only weak point is the TST control. I think that is one of the issues that should be controlled, because in practice we experience that let's say 10% of the TST is out of the limit values, and I think that's the next point that should be worked on. But I think as we are now, the gas quality is of the biomethane plants in the Netherlands is quite well, and the uptime of the plants is over 8,000 hours, and we can be satisfied what has been achieved in the last years. So that's my input. Thank you for your attention.
Thank you very much, Erik. And can we have the last presentation? Are you ready, Anton?
Thank you, Torben. I hope you can hear me well.
We hear you well.
Thank you also, Robert and Alexandra, for organizing this outstanding 60th anniversary conference. I've been involved in GERG activities for quite a while already, since 2008 with a small pause. I would like to talk today about the challenges we are facing in Spain regarding biomethane injection. To start with, I have to say that the biomethane injection in Spain is only at the initial stage. So there are two plants connected and to the transmission system for injection of biomethane, and that's only the second one is only very recent, and a handful of them to the distribution system, and also quite recent experiences. So first of all, the first technical challenge is the lack of homogeneity in the admissible conditions for injection in transport and distributions. Then there is also economical challenges in the sense of the absence of economical instruments that encourage the development of this market. There are no specific national feed-in tariffs, for example, as we will see. And then the regulatory and administrative burdens. There is fundamentally a need for a stable and clear legal and regulatory framework. We've seen from the previous presenters that we have very good European standards already developed, but these standards need to be translated into national legislation. And then the Spanish biogas roadmap on a policy angle, it's still in a draft stage, and it is lacking, from our point of view as main gas emission system operator, is lacking ambitious goals. Next slide, please. Yeah, regarding the composition, I think Erik from Kiwa has already give a very detailed overview of all the challenges, and also the other Erik. There is a point that I would like to emphasize, which is the standardization of the frequency for the quality measurement, for example, and the challenges next to oxygen, and the differences that there are between transmission and distribution standards. For example, in our national royal decree, the limit in transmission is more restringent than the European standard. and therefore it could be a challenge in the future if we have a reverse flow from distribution to transmission. This is derived from the fact that the European standards are not fully copied into the national legislation. Also, the responsibilities for measurement, it is not clear. There are different criteria depending on whether you are in the transmission or in the distribution network, which is always a challenge for the biomethane producer. And then regarding authorization, there's a need also to harmonize who's responsible for the authorization, not only for the installation, but also for the surveillance. Regarding the reverse flow, it is a problem that currently does not exist in Spain. And I would say, unfortunately, because that would mean that we have a lot of biomethane development, but it's not occurring. But there is already conversations taking place between distributors and TSOs and promoters to develop technical solutions. So if I would like to highlight something, I think the frequency and the parameters that need to be monitored is something that maybe an European best practice is needed, because we find, for example, that the requirements in our country are too limiting. They are just copy-paste from, I would say, an international connection of much bigger size for natural gas, and they should be adapted to the technical and financial capacities of biomethane producers. So let's go to next slide. Yeah, regarding support schemes, I think there is a lack of any of them. Basically, there is no feed-in tariff, there is no feed-in premium either. Even though we believe that if the national GO and certificate registry gets ready soon, there is already a draft decree in process, then that will be possibly sufficient boost to the biomethane market. So a very good working European-wide system might be as well sufficient if linked also to the ETS to encourage biomethane production. Regarding the tariffs, there is also a difference between transmission and distribution networks. The European Tariff Network Code, which is the one setting the general rules for all network tariffs in Europe, foresees potential exemption to biomethane injection points if they are on distribution networks but not on transmission network. So this poses a challenge because whether the biomethane is better injected on transmission or distribution networks should depend on the size of the plant and on technical grounds, and not necessarily be conditioned by incentives. From a hydrocarbon tax point of view, there is also a problem that there is no exception so far in the national legislation for biogas or biomethane. So all this contributes to the same to making biomethane development more difficult. Next slide, please. So then, from a regulatory and administrative point of view, the administrative procedures are complex regarding the application from the construction and the authorization procedures, both for the plant and the connection pipeline that you many times need to reach the distribution or transmission system. Regarding the regulatory framework, there is a need to update the regulation on energy planning according to this new energy and gas landscape with more atomized and delocalized, decentralized inputs. So that's not been taken into account in the current legislative framework and planning process. Also, the interconnection pipeline is a very important piece of a project. There should be also clear rules, whether it is part of the national transmission system or not, what should be the operating pressure, who should be the owner, and the lack of clarity makes every new authorization process rather complex. There should be also a sort of overarching authority or technical manager that gives clear guidance whether a project is better suited for distribution networks or transmission networks. We think that is lacking as well, at least in our country. Next slide, please. And that's it. So in a nutshell, there are several challenges from a regulatory, technical point of view. Perhaps I highlighted more these economic and regulatory aspects compared to the technical ones shared by my colleagues, but I think we need to overcome them all. Thank you.
Thank you, Anthony, and thank you to all of you. And I can see in the chat that there's already a lively debate. But is there someone who has questions they'd like to raise? Please raise your hand. It is a panel discussion, so please ask questions so we can have something to discuss.
Torben, I see the first question in the chat is from Eric Buthke to Annette on the discussion inside CEN TC408 about upgrading. I don't know, Eric, if you want to elaborate on that question.
Yes, it is interesting to see. We had first research in TC408 about siloxane content, and then we came to very low levels because for vehicle use, the impact of siloxanes on the oxygen sensor and other components in the vehicle were really impacting the performance of the vehicle. So we came to very low figures, and that was a concern because how to upgrade the gas. And then we found out that most of the upgrading facilities, upgrading parts of the plant are also taking out siloxanes. And I really want to know from Annette if that was also recognized in the research you are doing in Denmark about do you know if that is also for the other processes you are describing? I know that it's for the PSA pressure swing absorption, it's working very effectively, but how is it for the other processes you are describing? Do you know that?
No, I'm afraid I don't. It's actually not something we've looked into, but I have noted down that it might be interesting to look further into. We don't have a lot of biogas vehicles in Denmark yet, but it's a point that could be interesting to look further into.
Okay. And I know it is also part of the GERG project to at least do an literacy study for that. So yeah, it's interesting to know what the effect of the upgrading facilities is on the removal of siloxanes out of the biogas.
Eric, according to my knowledge, most of the siloxanes are removed by Colbert filters. That's the most common technique.
Okay.
But there's a limitation on it. If you have a high input, you can reduce it, but not to zero. So that was told to me. So okay. Let's say you can remove 90%.
Yeah, but then you are. But the conclusion was that you are then at a level which is acceptable for injecting and for use it as automotive fuel.
I have a question from Eric Bolman. You've presented very clearly the current practices in the Netherlands regarding how frequently biomethane should be tested, for example, for the smell. I sort of brought a different perspective on the topic and said maybe we are on paper monitoring too much in Spain. So how do you think we can find the right balance between properly controlling the quality and not overwhelming biomethane producers with very frequent checks?
Well, that's a hard question, but yeah, if it's only paperwork, then of course it doesn't work. So that was a bit of the input of my presentation. I think, yeah, well, now we do it once a month, and I think that's quite often, but you can experience it, of course. Yeah, you only have a few plants in Spain, so if you start with once a month, I think that would be a good start, and then you can always loosen it. Huh? You can tighten it or loosen it, but depending on the results, I think.
Thank you, but definitely should not be something comparable to what we have on a big conventional gas production field or a big interconnection point. I quite agree.
Yeah. In fact, biomethane needs more control than natural gas, because with natural gas you can do with the monitoring system you have. But I think with biomethane you need some additional control.
Yeah, do you have a requirement for measurement of the terpenes and so on after the cold bed filter?
No.
Or is it an option?
No, it's an option. It's an option the biogas producer does, because he doesn't like to be a disqualification of his gas. So that's a measure he has taken himself, and that's of course a good thing that the biogas producer is proactive in this field. But it's not an obligation. The obligation is that the gas has to smell correctly.
Yeah.
And you have to find means to come to that.
I noticed there was a question from Kathleen Putman, but I can't see the question in the chat because I think the font size is too big. I don't know if, Kathleen, you want to ask that question directly. It's concerning propane, I think.
Yes, I want to know what's the value to put propane into the biomethane.
I know
if one says they does it.
There is a lot of discussion about it in Germany. I know, especially for the vehicle part, because when you compress propane up to 200 bar for use as automotive fuel, the propane will become liquid if there is more than 7 or 8% of propane in the natural gas. So there is a limitation for vehicle use. On the other hand, if you use it only for industrial applications, there is no issue. But then where is your fueling station located? Where is it located on the grid? And if the propane content is too high, you cannot compress the natural gas for vehicle fuel.
From my side, I'd say that well, there is not too much value in injecting propane to biomethane injection stream. I guess it's because of the calorific value control. Yeah. But I think we have already within the industry and with the development of IT, sufficient and alternative ways to handle calorific value variability in terms of billing and also in terms of process control. And I think with the advanced production techniques that Annette has shown, I think also we can have very good quality biomethane that does not need addition of fossil fuels.
Yeah, good go. I was wondering how much, which questions have you had to the two biomethane standards from the industry? Where is the, I mean, where are the obstacles that are experienced out there?
Now, it was during the whole standardization process, it was very interesting to see that on one hand, you have the gas industry, which want to sell the gas. And on the other hand, you have the, especially automotive industry, who wants to have a very narrow specification for the use in vehicles, because then they can optimize the performance of vehicles. So it is a real competition between distribution of gas versus specifications of the gas. And yeah, that is sometimes a challenging discussion. And but I think in the end we came to a good consensus on that. There are still some open questions, and that's also the reason that we want to have this revision, and that's also the systematic review will be open until June next year. So the national standardization bodies can vote for revision of the standard and give their input for the needs of the revision of the standard. So I want to invite also all relevant parties to take part in this revision, and also to contribute to the work group to set up the revision of those standards, and to become active in those working groups.
Is there more questions? We have time for a few more questions. Or is lunchtime more attractive to continuing the process here?
I still have a question. I have translated it for myself because it's not always so easy to speak English. In Belgium, we are not so favor of having the producer letting other resize. The other one is a dangerous substance, and in the case of smallest problems, the network operator is looked at. How do you deal with this? It's mostly for Eric. I know the producer is authorizing in Netherlands. How do you deal with problems?
Yeah, well, of course, it's a matter of the law. He is obliged to authorize the gas, and he has obliged to do it himself. So that means that we can change that, of course, and he has to have precautions, of course, for safety. But I think that's that's not the gas law. So I can't say much more about that. Of course, you have to be very careful with authorization because it's. But it's his responsibility, and he has to deal with it.
When you shouldn't have a law, what would you prefer?
I think it would be good if the let's say the grid owner was responsible for the authorization and for the final control, like in Germany. I think that that would be the best solution, but yes, that's my answer. I think if you only merely look at the gas quality control, it would be good if you if experts would deal with that. So that means, for example, grid owners, they do the final control and the authorization.
Okay, thank you.
then I think I will say thank you, especially to you, the panelists, and to all of you participating and posing questions. I think it's been a very good day with a lot of information, and yeah, the process continues tomorrow, where we have the third day of celebration of the anniversary, and it's hydrogen, which is on the agenda tomorrow. So do you people from the Secretariat have a final remark before we close the session?
Yes, thanks, Torben. I'm not sure if Mures wants to say anything as well, but I would just like to thank everyone who's taken part today, and the speakers for their contribution. Maybe again the Secretariat who've been involved in organising this can put their cameras on, so we can see who they are. That will be good. Magdalena and Miguel. I know Antonio thanked Alexandra and me earlier, but actually it's been these three, Alexandra, Miguel and Magdalena, who've been doing all the hard work behind the scenes and doing a great job, as I said yesterday, and I will say again tomorrow. I thank them very, very deeply for the work they've done in organising this conference and bringing you all to the table and publicising and promoting GERG at this point in our illustrious life, this milestone, not just a milestone in that we've done 60 years, but I think it's a milestone in that we've also gone through this strategic reorganisation and focused on strategically what is very much in line with the European Green Deal, the biomethane, methane emissions and hydrogen, and have brought these roadmaps to the fore. And we're hearing today, it's been a really good set of presentations, and we've heard a panorama of interesting work that shows that collaboration is still at the heart of what we need to do. The projects, the roadmap, the projects we heard about this morning, the flagship, the PRCI collaboration, the potential for bio-LNG. This afternoon here, later in the morning, hearing the very broad and coherent spread of views on the panel. We see there is still work to be done. There's an established industry. We tend to forget that biomethane is probably going to have a greater potential and in the short to medium term than hydrogen. There's much focus on hydrogen, but the potential for biomethane in supporting a circular economy and reducing emissions and potentially being even carbon negative is huge. And we need to make sure that we do what we can to enable that industry. And I think that's what we're seeing today, is that the number of views around this conference and the potential other things that we should be considering. I mean, Robert Ziegler mentioned the bio archaea type approaches to producing biomethane. There's a lot to think about and a lot to keep us busy as a research organisation. So once again, I thank everybody. I thank the Secretariat again for the work they've done, and I thank the speakers, and I thank everybody for turning up today and listening. And I hope you've had a great morning. And thanks, Torben, for moderating and for leading the working group and bringing the roadmap to the fore. So, as you say, tomorrow we're going to do more of the same. It's a longer day tomorrow, but there's a lot to cover, and I hope you will all turn up again tomorrow for a really good discussion about what we're doing and what's going on all around the world. In fact, on the hydrogen front, and I know that's of great interest, and we're looking forward to that. So thank you, everyone, and have a good day.
Thank you. Have a good day.
Thank you. Have a great day.
Bye. Thank you.